All right. So thank you for sending in your topics. Survi gave me the topics, and I just quickly, prepared a very quick presentation for you all. So it's very to the point, and I didn't have very much time, honestly, because I just finished my work. So at any point you have any question, just let me know. I've planned it in a such a manner that we'll invest like 45 minutes for you to, I mean, for me to walk you through those certain topics, starting from the type of machine learning, supervised versus unsupervised, descriptive stats, where we talk about the various data distributions and how a different charts like bar chart and the scatter plots and the histogram. And then we talk about the type of data, and then we talk about the type of algorithms. Now, basis the feedback that I've received from Surbhi, that you all are non-tech people mostly, and it is getting too complex for you to understand some of the technical terms. Now, the way I am planning to deliver this session is that, to maybe help you resolve your queries since your exam is coming up, and also deliver in such a manner that you are able to absorb the knowledge. So basically, we'll talk in very layman terms, like a business terms, so that you're able to understand it. Okay, let's make a start. So starting from the very first thing, which is the main topic, supervised versus unsupervised versus reinforcement learning. There is one more category in this, which is called semi-supervised, but that's not the part of the discussion today. So let me talk about the supervised learning first. I hope you all are clear with what machine learning is, or do you want me to start from that perspective first?
Start from that, sir.
Sorry,
You can give an overview of machine learning.
Yeah,
Okay,
absolutely.
okay.
Because most of us don't know what exactly machine learning. Might be, but not exactly what it is, right?
Okay, makes sense. Okay, I'll start in a very simple fashion. So machine learning is basically, as per the definitions that we have read, is basically we are teaching machine to do something on our behalf. Now, how do we learn, right? If we learn the alphabets, then we learn how to make words, and then we learn how to make sentences, and then we learn how to write paragraphs, and then we learn how to write a story. So basically, machine learning acts in a similar manner. It's kind of an artificial intelligence. But again, how is it an artificial brain? Is it an artificial brain? No. Machine learning is basically using mathematics at backend to deliver artificial intelligence like results, just to mimic ourselves. So every decision we make is based on some past input, right? Or somebody has taught us, whether it's learning to drive or taking a decision in life, whether to go out to our office between 8 to 10 versus 7 to 8. So this is something we have learned and have stored. So basis that learning, we are taking a decision. And when we try to, mimic the machines do that, certain code, so machine is nothing, just a code, just a piece of code. When you add it to a hardware, it becomes a robot kind of thing. But something we make a code learn and make it do something. That is what machine learning is. So there is no rocket science in it. It is just, and at the back end, it's all mathematics. It's all mathematics. For example, we all have learned that identity, that a plus b whole square is a square plus b square plus 2ab. It is just a mathematical expression that if you add two quantities a and b and take a square of both, the expression can be broken down into a square plus b square plus 2ab. So basically, any number you can put in that formula and find a final output. So that output is basically an inference or a prediction. So that's how machine learning works. Now, machine learning, as I said, it's divided into three major parts: supervised, unsupervised, and reinforcement. A lot of machine learning is so this topic entirely is in a way, mimicking humans behavior. So as the term suggests, supervised. So it is like, teaching a computer with examples. So for example, imagine you have a friend who is learning to identify fruits. It's a very, small kid. Now you may show your friend many pictures of apples, oranges, and bananas, and you tell them that which fruit each picture is. Say, this is apples, this is bananas, and this is how oranges look like. Now that your friend or your kid starts to notice patterns by themselves and differences among these fruits, maybe the color, maybe the taste, or maybe the shape of them, right? Maybe the weight of them, how to peel the fruit and eat it. Then later, what you do is you give your friend some new fruits which they haven't seen, like a watermelon or mango. And basis the knowledge that you have given in past, they confidently tell you that each fruit is based on what they learned from the examples. So they'll try to weight it, try to peel it. So it can be a vegetable as well, but basis the his experience, he may be able to tell you whether it's a fruit or a not. So likewise in supervised learning, the computer works in a similar way. It learns from a labeled examples and can make predictions or decisions, or we can call it inferences about new unseen data. So that is what supervised learning is. So in this slide, I've labeled data. I have like different figures, triangles, squares, and other polygons. Then we label them like triangle, square, and hexagon. We put the information in a model training. Now we'll talk about these models later on. These are basically certain algorithms that have the capability to do this prediction. Basis, and we provide a label data. So basis this data, the computer or the code is able to learn, okay, this is these features, it is called a triangle. This is n number of features, it is called a square. This is n number of features, it is called a hexagon. And then it creates a model. Okay, it's a mathematical relationship. When I say it's a training, it's a mathematical relationship that gets created. Now, whenever a new data point comes into action, what it'll try to do is it will try to compare it with the parameters or the variables or the qualities or the columns, as we say it, of hexagon with triangle and square. So whichever is the closest match, basis the mathematical function which has been defined, it will assign that label to that unseen figure. So that's how the supervised learning works. Now, this is about the supervised learning. Now, what is unsupervised? So unsupervised is basically, it's like, finding the hidden patterns without any labels. So I show you something X and I ask you what it is. You can try to make n number of guesses. Say, I think it's a pen, or it's an object, or it is something else. Anything. Like you're just trying to make wild guesses basis certain information that you already have, right? But since it's an unsupervised learning, sticking to definition, imagine you have a box mixed up with mixed up puzzle pieces, like in this picture, and you don't know what the final picture should look like. So what you do, you start sorting the pieces based on maybe, let's say, colors, maybe let's say shapes, maybe the patterns you notice. So a teacher gave different kind of objects to a kid. What the kid does is blocks are arranged based on color, maybe arranged based on shape. Now, once you start sorting the pieces based on colors, shapes, and the patterns you notice, eventually groups will be created and certain groups will emerge, either one or two, depending upon what I've provided you. So this is how the unsupervised learning is. There is no pattern. There is no fixed number of classes that the data can be divided into. But eventually, the computer examines the data, and we apply certain algorithms. So there are certain algorithms which work in supervised learning and which work in unsupervised learning. And these algorithms, they examine the data, apply the mathematics, the intuition behind, and they label and try to group similar things together. And it can be basis the parameters of the data that we have given. Okay, so that's how we discover patterns or relationship that we might have not noticed on our own. A very common example is consumer segment. So when we're trying to, segment consumers, you know, we try to create clusters of consumers which might predict in a similar fashion. Certain areas you can think of where the consumers might behave in a similar fashion, maybe their demographics, the region, their geography, maybe their religion, maybe their choice drivers, their preferences, where do they like to eat, right? Do they like burger more, or do they like chicken more? Are they vegetarian or non-vegetarian? Do they like pizza more? So in a nutshell, supervised learning is like teaching with examples, while unsupervised learning is like finding the hidden patterns. So that's how, both the methods help computers make sense of data, and there are and do certain tasks which can be very helpful, like recognizing objects in pictures or making suggestions based on what they have learned. A very good examples of supervised learning is making predictions for, you say, stocks, or predicting the weather, how the weather forecasting is going to be basis the past movement of the monsoon or the other parameters. Unsupervised can be, the very popular example is customer segmentation, how the consumers are, behaving in certain segments. So there can be 4 segments or 5 segments or 7 segments. We don't know, since it's a unsupervised learning. In each and every segment, consumers might have different characteristics, like, they have different willingness to pay for the food they're going to have, their preference over the brands, like either they want to go for KFC or they want to go for McDonald's. They might be coming from different economic zones, different professions, and that's how they are, converted into segments. So this is a very common and very popular use of unsupervised learning, the segmentation. Now, the third part is reinforcement learning. So reinforcement learning, as this picture suggests, is, teaching your dog new tricks. So let's suppose you have a dog named Max and is very playful, and you want to teach Max a new trick. And let's say it's just, throwing a ball, and you want the dog to go and fetch the ball and bring it back to you. Now, talking in technical terms, it is like we define a function. We define a function. Hey, whenever I provide a plus b, you need to do a square and provide me a square plus b square plus 2ab. So this is something you need to define through the algorithms. So again, we go back to the objective function where we have to define something and tell the algorithm, hey, this is the thing that you have to either maximize or minimize. Let's take a real example. Suppose you are, taking a business decision on your menu. You run a restaurant and you want to change the prices of certain items. Definitely, you want to increase them. And on some items, you are able to reduce the prices as well. But your final goal is, I want sales maximization. I want revenue maximization. So that's how we define the objective function. Now, coming back to this dog, how do you do it? You do it through reinforcement learning. One way to do is optimization as well. But talking in terms of reinforcement learning, what you do is you show Max how to do it. Okay. So the thing is, you throw a ball and you go to the ball, come and fetch it, bring it to Max. And then when Max grabs it and points towards you, take the ball out, give him a treat. Now, the treat is a reward that Max loves. Now, Max wants those treats. So what Max sees is, hey, whenever I pick the ball and provide it to my owner, I get a treat. And Max wants those treats. And since returning ball is providing me a treat, so no matter wherever the ball goes, I as Max should go there, fetch the ball, bring it to my owner. So this is where the reinforcement part of the learning comes in. That Max now knows what needs to be done and what's not need to be done. So now, but of course, dog doesn't know the exact sequence of steps to get the treat. So he tries different ways. He maybe try different actions. Sometimes he gets the treat, sometimes he doesn't. But eventually, his brain learns, hey, the objective is to get the treats. Okay, so whichever function, whichever way, whichever step helps him reach towards the treat is something that his brain will keep. The rest function it will discard. So that's how the dog completes the whole trick and he gets a treat. So this is basically trial and error. This is trial and error, and the dog learns the best way to get those treats. So reinforcement learning is essentially the same thing. So the very popular example is self-driven cars. where the computers, instead of treats, the computer gets a same term. I mean, it's called a reward signal actually for the good decisions. So we define an objective function that you have to drive a car, you should be in lane, the consumer safety is very important. Everything in a mathematical fashion when I say this. Okay. Nothing is added like in a objective manner or a subjective manner. Everything is converted into an equation in the universe of machine learning. Since we all are product and function of mathematics, so that's how machine learning also works. So just like maths, we define the objective for the auto driving autopilot for the car, and the computer, the code or the algorithm learns which actions lead to positive outcomes and adjusts its behavior over the time to get more rewards. The rewards we define in the term of reward signal. So this is all done mathematically. Okay, the objective is defined and the reward is defined, and the algorithm is chosen in such a manner that it will maximize the collection of reward points that the algorithm will get at the end. So
Yes,
in a
Sachin,
nutshell, yeah,
just
yeah,
interrupting you in between. So just to summarize about reinforcement learning, you are trying to say that it reacts to an environment where in which it will react on its own.
yes, yes,
Okay.
exactly,
So the algorithms will be like applied in the sense it will be set up in a way that it will be reacting to the environment on its own, just like you took the example for driverless
exactly,
cars.
exactly. They will
Okay.
interact on their own. It's all trial and error. So see, one good example could be, since we define an objective function for a self-driven car, is that you have to take a passenger from point A to point B in the minimum time possible. One anomaly that could come out of it is that the objective function, what it does is that, hey, if I break the lane, I'll just take the shortcut. So that is something that is also can be done, is possible, and the reward is maximum. So we have to define the constraints, the steps, the good rewards and the bad rewards in such a manner so that the algorithm will interact with the environment in many hit and trials. Okay, whether to overtake or not to overtake, how much speed should I, should the algorithm should keep. So that's how the reinforcement learning works. It's hit
And
and
will
trial and the
will there
rewards.
be a different, always will there be a different start and end state for each of the I
So
mean,
uh, yes, see, start is always random, but
mhm.
eventually it tries to reach to that. If I talk in the mathematical sense, it tries to reach to the global minima. Suppose you're standing on a mountain, okay, and so I'm taking a different example. You're standing on a mountain, and the objective is to reach the valley, and you have a, not on your eyes are covered, you can't see, you can only feel the gravity. So what you do is you will eventually start walking towards the descent part of it, right? You will take a step. If you feel your altitude is decreasing, you're going down, you will keep going until it doesn't. So you'll change your direction the moment you start again going upwards, right?
So
So
we
it's
will
hit
be
and
taking
try.
different paths.
Exactly, you will be taking different paths every time. It's not fixed. But yes, eventually, once, so let's say you took path A, B, then you took X, Y, then you took some different paths. So eventually, one of the objective function was to reach there faster. So whichever path you took the least time is the best optimum path, right? And that's the series of steps that would be taken as the gold standard to achieve this outcome. And that's how we, optimize our models, hone our autopilots, hone our self-driven cars. And eventually, if you would notice, that's how our decision making also works. So our all decision making in our life is reinforcement learning. Hey, it's raining, and or maybe it's probably 8 a.m. Should I leave for the office? Yes. If I leave now, I'll reach by 8:30. If I leave 10 minutes later, I might have to spend extra 30 minutes in the traffic. So that's kind of a learning that we are doing and are making our decisions based on that. So it's a combination of supervised but reinforcement learning as well. That all the decisions we take in our life, it's part of reinforcement. So next
Sir,
time you want to travel, you won't think it's 8 a.m. You'll just hit the road.
sir, as you told that these are mathematical inputs, the model will learn from the mathematical inputs. So, will the model self-learn anything from its mistakes and all? like the AI
Model,
do.
yes, yes, exactly. So in case of reinforcement learning, say since you have defined a reward, okay, that plus
Okay.
one for this action and minus one for the wrong action, which is not towards the optimum goal. And the objective of the algorithm is to get the maximum rewards. So whichever step, whichever series of steps gets him the maximum rewards, that is what the algorithm will choose. It doesn't mean that every time it will go for plus one, plus one, plus one. Let's say it goes for plus one, plus one, plus one, and eventually it gets into a valley where it's like minus 30 throughout next 30 steps. It won't do that. It
Okay.
might it might do minus one initially. That algorithm is seeing that in future there is a big positive reward waiting for me if I take two negative steps here. Okay, so that's
Okay.
also how reinforcement learning works. It's the
Okay.
optimum path at the end. Okay. All right. So we talked about the supervised learning, unsupervised learning, and the reinforcement learning. So supervised learning is further broken down into two parts: classification and regression. So classification is nothing but predicting something which can be classified, categorized, and regression is predicting something continuous. So for example, the mileage of what would be the mileage of my car based on certain variables, how much a salary person can take home if he or she has this features. Will I crack this exam or not, given what kind of preparation I'm putting in, what resources I'm following? So that is classification. Now, in unsupervised learning, as I said, there is no set pattern. We're trying to find the patterns or the clusters or the groups or the segments. So this is done on unlabeled data, and the most popular algorithms are the clustering algorithms, which are in unsupervised learning. No, so see, clustering is also a kind of a classification if you take in this manner that, how can I put consumer into three clusters or four clusters? So eventually I'm classifying a customer now, whether it belongs to a group one or to a group three. But since there's no label data to it, that's why it goes into unsupervised learning. Otherwise, once you have a clustering algorithm with you, you have defined labels for consumers. Next time you have to predict a customer, you will use the same model, but then it becomes a case of a supervised learning, not the unsupervised, because you had some past data. So yeah, that's how it works. Now we'll talk about certain, the data. So I think this has been covered in your theory already. What is data? So anything which gets recorded for the purposes of, you know, for the purposes of, I mean, for various purposes, I'm sorry, it is data actually. So, I mean, it can be a number, a sound, a picture, uh, audio, we already talked about, a sentence, a paragraph, a comment, everything is data. But talking about data, it can be broadly categorized into two parts. It can be either numerical or categorical. Ideally, it should have more categories, that it can be sound data as well, or it can be text data as well. But if you will, eventually record that data, that is essentially recorded in a numerical manner. So broadly, data is of two types: numerical, categorical. Numerical, as the name suggests, made of numbers. Anything like age, your weight, number of children, shoe size. It's a numerical data. Categorical data made of words or classes. So eye of your color, your rank, your gender, your blood type, anything. So categorical data is further divided into two parts. Your eye color can be blue, brown, black. There's no order to it, right? But there are certain things which have an order to it. You either you were satisfied, or you were delighted, or you are unsatisfied. There's an order to it, right? Delighted, satisfied, unsatisfied. There's an order to it. So whenever the order comes in the categorical data, we call it the ordinal data. So it's basically a hierarchical kind of a data. Now, the other part is nominal, where there's no order. You can just talk about in any sense: blue, brown, black, black, blue, brown, anything. Likewise, we have numerical data. So numerical data can be of two parts. It can be a continuous number, anything was like 1.2. So it has a decimal, and then you have succeeding terms as well. Or it can be discrete, finite. 0, 1, that is the binary data, or shoe size. So you can't have like 7.2 is your shoe size. It's either 7 or 8, the scale that we use. Although I strictly believe the shoe size can vary from either 7 to 8, we have 7.5 as well. So that's not the right example for the discrete. The number of children, it cannot be 1.5, right? It's either 1 or 2 or 3 or 4, whatever. The continuous is again your blood pressure, your age, your weight. So, and why is this important? Because, basis the kind of data in your algorithm, the data you have, and the problem you're trying to solve, your um, your choice of algorithm will differ. Your pre-processing steps will differ. Your outputs will differ. So that's why this is a very important aspect of machine learning, the data. Now, talking about the numerical data and how it is presented in descriptive stats. So for the sake of understanding, I've taken only one chart today, which is the histogram. So histogram is basically, it's a univariate chart. Univariate. Uni means one. Single variable chart. Now consider it is the income of the people available in this group. So, and let's say, and it doesn't have to start from zero. It can start from 5 lakhs, 10 lakhs, 15 lakhs, and go as high as 50 lakhs, 60 lakhs, 1 crore, whatever it is. Now, when I try to break it down into certain number of bins and take a count that, hey, between 5 lakh to 10 lakh, how many number of people do I have in this group? Between 10 to 15, between 15 to 20. So with every increment of 5 lakhs, what's the number of people do I have? And the bin size, the width of the bars will remain the same no matter what. So there are different kind of histograms as well, where the width can change, but that's not the part of your course right now. So just stick to simple histogram. Now, eventually, when you plot this distribution, so distribution is basically plotting the data in a descriptive manner through a statistical chart. When you plot this distribution of the salary, there are three charts possible. Either the chart looks like a bell curve or the right-tailed. So this is like, it's tailing towards right. So that's why it's a right-tailed, or the tail is towards left. It's a left-tailed. Every chart has a characteristics, three characteristics, which is like the essential statistical characteristics: mean, median, mode. Mean is nothing but the sum of all observations divided by the total number of observations, the average. So we use this word very frequently called average. There is the word called mode. So the maximum number, where does it lie? In which bin does it lie? What is the maximum number of gender in this group right now available for this call? So that would be the mode, either male or female. The median is basically, if I ask you, what's your, let me think of an example, median. Okay, what's your shoe size? Let's start asking the shoe size. We have like 15 people will have number varying from 5 to 8 to 9. So whichever number has the maximum occurrences, that will be the mode. But if I just plot the number from, in an increasing fashion, in an ascending order, whichever number is in the middle, that will be called as the median. So a symmetric distribution or a normal distribution is where when mean is equal to median is equals to mode. Okay, and it looks like this. A right skewed distribution or a right tail distribution is whereas the mode is more than median and is more than mean. See, the one reason mean is getting deviated now from here to here is because you have many number of observations which are low in number, but they have high magnitude. So magnitude is increasing when you go from here to here. So that's why mean is being pulled towards it. So that's why if you have outliers in your data, we try to do the mean imputation mostly, because we try to put back mean to where it belongs and convert this distribution into this distribution. Likewise, you have left tail, where mean is less than median is less than mode. And again, I'm sorry. Yeah. So again, why mean is towards here and not here is because since you have a lot number of data points towards this where the magnitude is low, and that's why they're pulling mean towards the lower number. So that's why mean is low. See, one thing I'm just telling you right now, it's not for your course, but for your data processing journey, if you pursue data science, is median imputation is the best imputation instead of mean, because if you just notice, median is least affected by this right skewness or left skewness. Why? Because either way you put the data into descending or ascending order, median varies rarely. So that's why we go for median imputation as well, depending upon the use case.
By definition, also it lies in the middle only.
Exactly. So it's least affected by the outliers. So that's why we go for median imputation instead of mean. See, mode imputation is useful in the classification data when you have multiple shoe sizes and you have certain missing points, and you just want to predict where the distribution might lie, where the missing number would lie. So you can go for the mode imputation in that case. Okay, so we talked about how a numerical value can be represented. Now let's talk about how. Okay, so sorry, this is a comparison between a histogram and a bar chart. So this is how a numerical value can be presented. So how a bar chart works is, so it looks similar to a histogram. If you just notice, there are certain gaps to it, and the reason for gaps is because the one value is count and another value is a class. So initially we were plotting down what's the shoe size, or let's say what was the salary. Let's suppose we classify into, so we all come from different states or cities. So let's suppose we classify into a different problem where we write down, for this X city, the highest package is this. For the Y city, the salary is this. For the Z city, salary is this. So now you have classes to it. And classes can be in any order. It doesn't have to be A, B, C, D, E. It can be B, C, A, E, F as well. It doesn't matter. It doesn't have to be in an ordinal fashion. But when you talk about a histogram, since we're talking about bin sizes have to be, since I said this is a normal histogram, bin sizes have to be of equal length and they can go in a progressive manner only. So that's why it's 0 to 5 and 5 to 10 and not after 0 to 5, it's not 15 to 20 directly, because the bin size will differ. So bar chart is used when you have one categorical variable and one numerical variable, or you're trying to find the count, or mostly it is count actually, for a categorical quantity. So this is where the bar chart kicks in. But when you're trying to see how the distribution of a numerical data looks like, always go for histogram. Now, what if you have two numerical values, and how do you look at it? So the previous charts were all univariate analysis, one variable at a time. The bar chart is kind of a bivariate, but since here as well, since I am only talking about the categories, and let's say it is a count, it becomes into a univariate analysis only. If I add another category, I'll have other versions of bar charts that you can Google up, like stacked bar chart, or you have group bar chart as well. Now scatter plot. So scatter plot is simply, you put a x-axis, you put a y-axis, and you put for every x what was the y value, or vice versa for every y what was the x value, and you plot all the points. Okay, so one example can be the height of a person and the age, or maybe the weight of the person and the age. So as the age is increasing, the weight of a person is increasing, and after a certain age, the weight starts decreasing, right? It happens in old ages. Not always, but it happens. So once you start noticing certain patterns in scatter plot, there is another word called correlation. So as the name suggests, correlation, that two quantities or two entities are correlated, that change in one quantity affects the change in other quantity. It can be either positive or negative. Now, here I see that there are two quantities. If one is increasing, other is also increasing, which is nice. So I can say, yeah, it's a strong, first of all, it looks like a very strong relationship. We are not quantifying it. It's only a subjective analysis. If you want to quantify it, we'll go for the correlation coefficient. The second is it is positive. If one is increasing, other is also increasing. So that's why it's positive. Now the third term, which is linear. So don't get confused. Linear is basically line, a straight line, simple line. Remove this air. It's a simple straight line. That's it. If it's a non-linear line, this is where we call it a non-linear here, or we call it a polynomial. That it's not a simple equation of a line. It has like x square or x cube, a certain degree to it. Likewise here, in the opposite fashion, this chart is working, that one quantity is increasing but the other is decreasing. So the y-axis here is decreasing for every increasing magnitude of x. So I can say it's a negative correlation, since again I'm not quantifying it. This is not the best way to calculate the correlation. It just gives you an intuition. That's why I wrote correlation intuition. But to quantify correlation, you have to go through the statistical formula of it, of the two values. So there's a proper formula for it. Here in this chart, I see a random pattern. So there's no relationship I can talk of. Again, this doesn't signify that there is no correlation at all. See, visually I see no relationship, but if I go for correlation, there might be a possibility it might have a correlation of like 0.2, which I can say it's a very weak correlation, and that this is what the chart is signifying. But again, it doesn't mean the correlation is zero. No, it's not like that. Okay, so far, like we covered descriptive stats and the intuition of data, and we covered what is supervised, unsupervised learnings. Now the next part is it will get more technical. We'll talk about different algorithms in a very layman terms only. So different algorithms. What is prediction / inference? Why do we need prediction? So prediction is basically predicting a quantity, finding out a quantity basis certain features of that problem we have and certain learnings we have from past, that okay, basis this feature it can be this or it can be that. Now what can we predict? I mean, so why do we need prediction? So that since in our pursuit of this modern economy, we're trying to get ahead of everything. For example, how the consumers will behave if I
HM,
launch this.
Sorry, but your voice is breaking, and
My
somehow the
voice
voice is
is
not coming.
okay. Is it for all or?
It's fine
No,
for me.
No, it
No,
is
no,
fine.
Fine.
it's
For
fine
me,
for
it's
You
us.
need to
okay.
check.
For me, your voice is very clear. No.
Okay.
For me too.
So probably I think you might need to check once. Sorry. It's working fine. Okay. So why
It
do
is
we
okay.
need
He need to
prediction?
check his connection.
Yeah. Okay. Should we continue now?
Yes.
Okay.
Please.
So we were talking, why do we need
Is everybody
prediction? So
facing?
sorry, I can't see if you're saying something. I mean, do you want me to wait or do you want me to continue?
No, I thought everybody's facing issues. Like they're not able
Every,
to hear.
Acha, okay. I thought everybody is fine with it. So
I'm not
let
sure. I'm just asking everyone. Is everyone facing issues with the audio?
No. We are able
No,
to
no.
hear.
Clear.
No, no, no,
Okay,
no.
okay,
There is no
Audio is
problem with the
very
audio.
clear.
okay, okay.
I
I
think
think it is at your end only. You need to check.
okay, let's continue. So why do we need prediction? So as I was saying, in our modern pursuit of economy, one very good example is we're launching a product and you just want to understand how the consumers might react. Now, this is kind of a consumer behavior thing. And if I'm able to predict that in advance, it is very much possible that I can change my strategy of launching that product. On which dates should I launch the product? At what time should I target my consumers through the promotional emails? Which consumers are likely to open that email, so I should send that email to those consumers only. So this is how prediction can help save us a lot of good money actually, which can be utilized in other efforts. And Yes, so that's all about the prediction. So I'm just taking examples from consumer industry because this is where I've worked mostly. Now, what can we predict? So we can predict. So since I talked about that a categorical data or numerical data, so we can predict anything which can be solved through a categorical data or a numerical data. Whether we can predict how the stocks will perform over the days, whether we can predict how what's the probability of an event to occur, and that is like very good use case that we're using right now. So one example is propensity models. If I'm able to predict what this X person is likely to buy on coming Friday, the probability of it, is it like a very good use case that I should start sending a targeted email to that person that, hey, there's an offer for you to buy this particular product, the particular product for which I got a propensity probability through my prediction, and I may be able to increase the chances of that particular transaction to happen maybe earlier or possibly very well on Friday. So that's how the predictions are helping us solve the problems. Now, what can we predict? So I can predict when you're going to buy something, what time you're going to buy, how much amount you're going to spend, and what item you're going to buy. So that's how we can predict almost anything, like a categorical value or a continuous value, anything that solves our problem. One of the use cases of different algorithms is the sentiment analysis, where we try to analyze the sentiment. So this is not a part of prediction or anything. It is pure text analytics, where we run the text data through certain algorithms, and we try to find the kind of polarity of the sentence, whether it's a positive or negative or a neutral. So that doesn't come into prediction, but yes, there are algorithms which do that. But yes, I can very well predict, basis your transaction through a vendor or something, what's gonna be your satisfaction level. It's gonna be a positive, a negative, or a delighted one. Now, to solve these problems, there are different kind of algorithms available. So for every use case, there's a different algorithm. There's a propensity model, which is a kind of a regression algorithm. Uh, if I want to classify consumers into segments, there is clustering. If I want to classify, what are you going to buy, I can maybe use a classification algorithm. So classification is nothing but trying to predict what exactly which category product you're going to buy. So that's how the classification is. Now, I think these are the major algorithms that have been covered apart from the reinforcement learning. One is supervised and one is unsupervised. So supervised is the umbrella term for either regression or a decision tree. Then again, these tree-based algorithms are further, explained in different fashion. I mean, they have advanced versions of it, which are like random forest, XGBoost. Now, the broad term classification either have the trees algorithm, or you have like KNN algorithm, which stands for K nearest neighbors, logistic regression. So there are n number of names, so on and so forth. But what are these exactly? So every algorithm is basically intuitively, essentially following a mathematical equation at the end. So regression would be, a linear regression would be following a line. It's like a straight line equation and trying to fit your data to that point. A decision tree would be following a certain number of rules that, okay, if X, then Y, if Y, then Z, if Z is less than this, then A. So that's how it's a rule-based algorithm. Then there's a random forest, which is the advanced version of decision tree. I mean, that works in a more robust fashion. Then you have gradient boosting machines, which is like an enhancement on random forests or on the tree-based algorithms. Then you have and under classification algorithms. So mainly today we are going to cover linear and logistic, and probably if the time allows, we'll try to cover the a priori as well. So talking about two broad terms, two broad algorithms, linear regression and the logistic regression. Uh, Linear regression is like drawing a straight line through points on a graph. You have x-axis, you have y-axis, And since you all saw the scatter plot, so now just assume that you have a bunch of data points that show a trend, like a positive, strong relationship on the scatter plot. And linear regression is a kind of algorithm which will help you find a line that fits these points as closely as possible. Now, one question should arise is, why do we want to fit a line? So we're not trying to just fit a line, okay, how closely the line fits and how this line would help me. We are actually trying to fit an equation to that data. Hey, given, so it's like, y equal to mx plus c. This is the basic line equation of a line. This m and x is where the whole game happens. So m is the coefficient and x is the actual data point. And it can be like m1 xn, m2 x2. So you have n number of features. So x is already defined for you. You don't know how the y would be. And to solve this problem, you try linear regression. Hey, maybe I can model this relationship into a mathematical equation, y equal to mx plus c, where m and x can take multiple values, m1 x1, m2 x2, mn xn, plus there is an intercept. Now, the thing is, you don't know, you know this x, but you don't know this y. So to find that m, which will complete the right hand side, you use this algorithm called linear regression. So linear regression will give you that m, whom we call certain coefficients. We call them coefficients. So one example we can take is, let's suppose you want to predict the salary of a person. So salary of a person can be a function of the age, which I can say x1. I say the highest degree, whether graduate or postgraduate degree, or let's say the city where the person has applied for the job, or the where the person is working right now. Let's say city, whether it's Delhi, Bangalore, Hyderabad, Pune, because every city has a different income zone. Now, there is a certain intercept to it as well called C, that hey, if this person has this degree, this age, it definitely have itna salary to hoga hi. This person would have this amount of salary definitely. So that's how you can take the intuition of the intercept, the constant C. Now, linear regression would help you identify how much the age. So let's remove age. Let's call it experience. It's the more relevant uh, feature. So basis this relevant feature, experience, and the degree and the city, how much weightage should I assign to experience, how much weightage should I assign to degree, how much weightage should I assign to city. And if you want to add further features, you can add the college as well. It's coming from tier 1 or tier 2 or tier 3. So that would help me understand his his intelligence level at certain point, that yes, if he was in tier 1, he must have cleared an exam. If it's coming from tier 2, he must have cleared this exam, or may not be able to clear that exam. But if the person is coming from tier 3 and he has like a good amount of experience, it just outshines everything, right? So that's how you will use linear regression to find what would the salary of that person would be. So linear regression will always be used to find a continuous variable. How much score Virat Kohli will score, how much runs Virat Kohli will score in this match, what would be the salary of the person, of this X guy who is coming for a new job. He has this amount of experience and a degree in a city. How much amount of salary or the appraisal should we give to this person, or any continuous thing that you can think of. Any numerical data you can think of can be modeled into a mathematical equation and can be solved through linear regression. Now, linear regression is basically y equal to mx plus c. That what's the salary of a person basis his age. That's linear regression. When we start adding, multiple features to it, it becomes multiple linear regression. So in our real life, we never use linear regression. We use the intuition of linear regression and try to solve our problems through multiple linear regression, MLR. Now, another algorithm is logistic regression. Now, this is one of the very confusing one and a very popular one as well, which I think will be definitely asked in your exam, is logistic regression. That how is it a classification algorithm when it itself says it is a regression? So logistic regression, see, it uses a different mathematical form. If you just Google it out, you'll read it. You'll see linear regression has a different formula, and Logic regression is a different formula. And as I said, all algorithms are based on a certain mathematical equation that they follow. And this is what separates them. This is what, gives them the advantages or the disadvantages. Logistic regression would use the same equation of the line, but it will use certain exponent and there's an equation so that eventually the output you get will be between 0 to 1, and this output is the probabilistic output. Actually, it is actually the probability, the odds that you calculate. So if I say chances of rain are 60% and I say chances of rain are 20%, and I ask you that you have been given 2 days. On day one, the chances of rain is 60%, and the chances of rain on the day two is 20%. And I ask you a question, on which day do you think it would rain? So now you're trying to classify a rainy day versus a non-rainy day. You've entered into a classification problem. But basis that probability, I think you can make a decision that, hey, I think there's a 60% chance of rain on day one, so I would classify it as a rainy day. So this is what the intuition of logic regression is. It will find a continuous quantity only, but eventually that quantity will be used to classify something, to find a class for something, or to make a discrete decision. So that's why logic regression is a classification algorithm. But what it finds out is a continuous quantity. That's why it's a regression problem, because eventually it uses the equation of a line only. So when I say line, it doesn't have to use a, so there are different mathematical forms. There's a line, there's a circle, there's a parabola. Okay, so without getting too technical, linear regression is basically, as the name suggests, line. There's a polynomial regression which would have a line as well as a variable of a degree. So it won't have like m1 x1, it would have mx square as well. It will add certain features which will have a non-linear relationship. So, but logic regression, it uses the equation of a line, and you can have polynomial logic regression as well. So I hope this, helps you identify between the linear regression and the logic regression. So, any
Right.
questions? Just shout
Yeah,
out.
yeah. I have one question. Suppose example, I would like to monitor one pump, say some simple water pump, and
Water pump.
I have
Okay.
to monitor
Yes.
the data like when this pump will. This is the, basically I would like to understand the predictive analysis or the predictive maintenance when this
Okay.
pump will get failed. Basically, this is
Fail.
usually
Okay.
used in the industries like they have many
Okay.
equipments like pumps, motors, and
Okay.
basically it monitors the data when it starts, when it will stop. All the data it is
Right.
get collected, historical data
Right.
collects. So
Right.
which model or which category it will fall under?
Okay. So it will fall under actually classification problem. So eventually you're trying to find out at what point the pump will fail. It will fail to start, and at what point it won't fail, right? That's your
Correct.
final outcome. है ना?
Yeah. Basically, customer want to understand. Say, example, after 6 months, if I get to know this pump will get failed, then I will buy the replacement of that particularly
Exactly.
pump or the pump is just example. I would like say any
Yes.
machine.
Yes, any machine. Yes.
Yeah.
So it's a classical example of classification problem only that, basis the certain feature. So I'll just explain this answer of this question in two ways. First of all, it's a classification problem that you're eventually trying to find on a particular date whether this pump will fail or not, whether let's say in 3 months or 6 months or 8 months. If you're trying to find when this pump would fail in 1 month or 2 months or 3 months, that becomes a regression. So there's a difference. Now, when you're trying to find only that, hey, after 3 months, after continuous running of 3 months, would this pump fail or not, it can be broken down into two parts. What's the probability of fail? And basis that probability of fail, you can make a decision. Let's say you say there's a 20% chance this pump would fail on the 61st day, but there's a 70% chance this pump would fail on the 65th day. So on 65th day, you can declare this pump that this pump will not work. It would be a fail output for this machine. But on the 61st day, you might take that chance depending upon your business model. So eventually there are two ways to look at it. If you're trying to find on which day it will fail, time to an event, it becomes a regression problem. But if you're just trying to find on a particular date whether this pump fail or not, you should find the probability first and see if either you use a logistic regression or a decision tree or a random forest, anything. At the back end, the model will find the probability first, and then basis the probability, it will make a decision. So whatever threshold you have provided, let's suppose you have given a threshold of 50%, that above 50, it's a failure, below 50, it's not a failure, or above 60, it's a failure, below 60, it's not a failure. So that's how the solution should look like.
Hide the confidence interval also.
Yeah, it will help you, take a confident decision. Yes.
Hey Sachin, just interrupting you in between.
Yeah.
Just to give a brief overview of classification algorithm is nothing but you are trying to say that we are trying to find new observations on the basis of maybe some data, training data, isn't it?
Yes. Yes. Yes.
Okay. All these
classify
algorithms.
new observations.
Okay. We are trying to classify the observations in terms of all this KNN trees, logistic regression, all the algorithms.
So yes, so see KNN. So I actually took this picture from internet. So don't go by the words of it. KNN is a regression algorithm as well. So KNN is like it can do prediction. So some algorithms can do regression as well as classification. For example, random forest. So KNN is also that example. It stands for K nearest neighbors. It can do classification as well as continuous value prediction for you as well.
And in general, like how do we classify this new observation into? Either it's into classes and groups, right?
Right. Classes or groups.
Okay, which can be, as you said, yes or no or 0 or 1.
So if it's a binary problem, either A or B. But it's
Okay.
a multi-class problem, either A, B, or C, then it becomes a multi-class classification. So you have some algorithms which has the capability to multi-class classification. So I usually conventional ML doesn't have this. If you we usually do it through neural networks, but there is a way to solve this problem. So everything has to be think in a mathematical manner. Suppose you have class A, class B, and class C, and you have to use logistic regression for it. So you can break down this problem in an analytical manner that you predict class A is one class and class B is others, and you train another model B versus others, train another model C versus others. So now using three different logistic regression models, now you can do multi-class classification. But that's a very that becomes very complex. So yes.
Just interrupting you again. So we are using Orange as the data mining platform in our course, which we are doing. So these classes here you are referring to us. I mean, we are referring to as target variables, isn't it?
Yes, target variables. Something we are targeting.
Okay, got it.
So target variable is basically that Y that you're trying to find out eventually, and your
So
independent
these are
variables
nothing but the classes, right?
Nothing but the classes.
Okay.
Yes. So there are different ways to it. So eventually, whether you use decision tree, a random forest, or XGBoost, first it will calculate the probability. But for the sake of simplification, whatever the threshold you have given or not given, or what model have learned, so you have this flexibility to change the threshold as well. The model will classify the final outcome into class A or class B.
So let's unlike regression, like what would be the output variable of classification?
Output variable of the classification would be that variable itself. So let's suppose in your target you had class A or class B. So the output would be either class A or class B. In terms of code, it will give you 1 or 0, but you will get to know eventually that 1 belongs to class A and 0 belongs to class B. The output is 1 or 0. But let's say you had, an imbalanced data set. And let me ask you this question. Let's suppose you have 100 data points and 99 belong to class A and only the 100th observation belongs to class B. Now, let's suppose our model is trained and it predicts all the variables into class A. Even in that sense, let's suppose I've given I'm testing on the same data on which I trained. It predicts all the classes into class A. even in that sense, my model is 99% accurate, right? But that's not the that doesn't specifies that my model is a generalized model. It's a good model. No. So we go for other evaluation parameters like precision or recall. So everything is not fixed in machine learning that you just can't, say, okay, my model has done the classification. I'm sorted. I'm getting a maximum accuracy. Every evaluation should be done on multiple parameters always.
So it's nothing but in classification algorithm, we are taking the input with the corresponding output.
Exactly. It's a supervised learning case. Yes.
Thanks, Sachin.
Okay. So, okay, do I have another slide? Okay, let's talk about k-means. So k-means is essentially algorithm where, okay, I've covered linear regression. Let's talk about decision tree first, then we'll talk about k-means. So decision tree is like, making choices step by step. So imagine you're trying to decide what to wear. So you start with a very big question. Is it raining outside? Is it hot? Is it cold? If it's raining outside, yes, should I pick a raincoat? If it's not raining, you can ask the another question. Is it cold? And decision tree works the same way. So there's a different mathematical, formula or the equation that works for it. So for after every decision, it finds a number. So this number is actually called entropy, but you don't have to get into it. So it basically finds a number, and that number would have an intuition, either higher the better or either lower the better. If it's lower the better, then it would put its decision into yes or no. If the number is coming very high, it will say no, move to next feature. If the number is coming very low, then it will stick to that and then pick another feature. So coming to the main problem, what you should wear today. So you start with, let's say you randomly start with, is it raining? Should I pick a raincoat? Yes or no? If you say no, then the another question is whether it's cold. So that's how a decision tree also works. So they, kind of help a code or a computer make choices by asking a series of questions step by step. So eventually, whichever steps of questions has the maximum reward. I'll just put it in terms of reward, but eventually it is called a loss function. That whichever series of steps has that number lowest or certain mathematical equation that's working along the way, which is lowest, it will took that series of steps. And again, it's up to the user as well whether the user is getting the desired precision or a recall from that model of. So decision tree, so all the tree algorithms work in the similar fashion. Now there can be technicalities to it. You can have one tree, multiple trees. You can have certain variations in the way tree is trained. So for example, one very popular algorithm is XGBoost or random forest. So what random forest does is it takes the data, slices into, let's say, 15 different parts. And let's suppose you had like 100 data points and 5 columns. So what it will do, it will make random combinations of data points and columns. At a given point, it will not take whole data to train one tree, which happens in case of decision tree that you put all the data all together. In case of random forest, what you will do is you will take 5 observations, maybe 2 columns, and build a tree and do some predictions. Then you will do this eventually with another tree. You'll take 15 observations again, and but this time we'll take four features. So every data point is predicted through multiple trees. Every data point is predicted through multiple points, that whole data point. And at the end, whatever is the majority voting now for that particular observation, that is what the final outcome is. So that's how a random forest works. So it's basically a random picking of data, random sampling, and so it's basically called bootstrap aggregator. So bootstrap is kind of a sampling where you pick the random points randomly. But why it's called bootstrap? Because you're not taking all the features at a time. So that's why bootstrap. And aggregation, because it takes the majority aggregation. And now I said random forest can do prediction as well as classification. So for classification, the aggregation is basically major voting, the most votes whichever class is getting. And in case of predicting a value, Suppose we're predicting shoe size. So one tree predicted 7, one predicted 8, one predicted 7.5. So at the end, it will take a mean value. So that's how it is able to do. It does a bootstrap sampling and an aggregation. And aggregation can be used in two manners, either classification or regression. So this is the very good advantage of random forest, that it can do. It can solve regression problems as well. So basically, time when the pump will fail versus as well as when will the pump fail on a particular day. How is it different from a decision tree? No difference at all. It is a different way. So it is basically, instead of training one decision tree on the whole data set, you divide the data set into n number of combinations and you train 200 trees on it and you take out the predictions. Because majority voting is usually not wrong unless your data was biased. So even if your data was biased, in that case also random forest is able to handle it because it's doing a random sampling every time. So that's how it's able to handle it. Now, another popular algorithm is XGBoost, but XGBoost is an advanced version of gradient boosting machine. So GBM stands for gradient boosting machine. Now think of this as a bunch of friends trying to solve a puzzle together. So every friend represents a tree. So each friend is good at solving one part of the puzzle. And what they do is they work together. And each time a friend solves their part, they focus more on the pieces that are still missing. Okay, so it's kind of a team effort here. Now, gradually, what happens is the puzzle gets completed really well. So, gradient boosting is something like this. To put it in a technical term, I would say there is one tree which does some prediction. Out of 10 classes, out of 10 data points, it is achieving an accuracy of, let's say, 70%, but it is doing something. So it has not learned something really well and it's doing an error of 30%. The error rate is 30%. The other tree would come into picture, and what it would do is whatever 70% was predicted correctly, it will keep it aside, that data. It will focus on that 30% part and try to learn it and try to do the right thing. Try to make the right predictions. And let's say out of those three predictions, the next tree is able to predict one prediction in a uh, one prediction correctly. Now the other tree would come into action. It will keep aside those 7 and 1 and it will focus on those two observations and try to understand that data. Okay, if this type of data comes, two of my ancestor trees were not able to solve this. So that tree will focus on that two type of data points only. So it's kind of a additive learning. One tree, after that there's another tree, then there is another tree. So you see, it's kind of a random forest, but it's a different manner of learning. So the iterative tree is learning from the error of the previous tree. Now, one thing that can happen is they overdo it. They learn the data exactly how it is supposed to be. So eventually, what would happen is they will reach 95% accuracy or 99% accuracy. But that's not how the world works. We never have the best representation of the actual population, but what we try to do is we try to make a generalized linear model, like a generic model which will work on all kind of data distributions despite any biasness. To solve this problem, I'm not sure if it's on syllabus or not, there's a term called learning rate. What it will do, it will regularize the learning of the next tree, and then the next tree, and then the next tree. So eventually, let's suppose first tree was 70% accurate, and the other tree was adding a prediction of 10%. It will not add that 10% directly, it will add like only 5% from it. So the final additive accuracy is not 80%, it is 75%. And for that next tree, which was giving an accuracy of, let's say, 70%, we will only pick 2% from it. So that's how a additive tree works. And why this learning rate or regularization is important, because so that there's no overfitting, so that we ensure model is not just cramming the data that we've given to it. So overfitting is basically cramming what we have given without any understanding of the real world outside. And likewise, there can be underfitting. So yes, XGBoost is a kind of an algorithm which is prone to overfitting but not underfitting because we are doing additive learning. While talking about decision tree, there are chances of either overfitting or underfitting. So overfitting is basically cramming the data the way it is and just, so every time you give the data point, it will try to match it with the past observation and try to give you an output. Underfitting is basically not working too hard to learn the data. It's as simple as that. That you're not that the algorithm hasn't worked hard. Whatever parameters that we had given for the model to work, they were not able to define the fit that data into that particular mathematical equation correctly or efficiently, and they are just giving any vague value for any number that comes, any data point that comes. So that is called underfitting actually. So that's kind of a business understanding I can provide you for underfitting and overfitting. How do we find out in analytics how if a model is underfitting or overfitting? So the only defined, only best criteria to do that is whenever you train a machine learning model, you all know that we divide it into a trained data, a test data, and a validation set. So keep validation set out of picture. Think of trained data is what model have seen. Test data is something that model will see once it is trained and only once. On trained data as well, what algorithm does is, let's suppose 70% of the data is assigned for the training part. Out of that 70%, model will use only the 60% data. 10% it will keep so that it can make adjustments to it while training. So while training as well, once a model has a series of steps, it will try to predict the observation. So for every observation, there is going to be some error or some good accuracy. So every time it's trying to do a hit and trial on that 10%, it reaches a score. Let's say X score is X, that hey, this is my error rate, what I've learned from this data. Now, what you do is you give the unseen data to the model. If the error on the unseen data is a lot higher than what it was on the training data. So in training data, that 10% the error was X, and on the unseen 30%, the error is Y, and this X minus Y is a very huge number. Let's suppose on X, on the training, you were getting 90% accuracy, and on test, you were getting 65% accuracy. Then can I say that something has gone bad? Maybe it has crammed the data really well. That's why it was able to give very high accuracy on the train set, and on the test set is giving a very low accuracy. So this is a very this is a conventional case of overfitting actually. Huge low error on the train data but very high error on the test data. But what happens in case of underfitting? The model is not really working hard. So basically very high error on the train data and very high error on the test data as well. So 50% accuracy on train and 40% accuracy on test. So that's a case of underfitting. So every time you're training a model now, just prepare a spreadsheet in an Excel or something that, hey, my decision tree model 1 giving accuracy of 70% on train and then test, and you try different models, different hyperparameters for that models. So essentially you'll get to know where that gap is minimum. So you have two constraints: you should have high accuracy, or you can take precision or recall, any metric that you can compare pre and post. So the gap should be lowest and the number should be highest. So that's how you look at it, that how the model is underfitting or if the model is overfitting. How can we handle it? There are certain ways to it. Overfitting can be because your model is too strict to the data. It's trying to learn everything. So you have to make your mod lenient. Ki, hey mod, that please get relaxed. So there are ways to relax a model, that you tone down its hyperparameters, change some parameters in its equation. So these are called hyperparameters tuning actually.
So
And if you,
we are not
yeah,
making accurate predictions on testing data in overfitting.
exactly. So there's a very high error on the test data. Yes.
Okay.
Yes. And in case of underfitting, there is error on trained data as well as there is error on the test data as well. That means your model is just not good enough for this data. You should either change its parameters or use a more complex algorithm for your particular data.
So in the sense, we are not able to capture the underlying trend of the data, you are saying?
Underlying trend of the data, yes.
Okay.
Exactly. So that's about random forest. And so this applies to this, the way of checking underfitting, overfitting, it applies to all the algorithms in this part. Now let's talk about the supervised. So I'll just talk about k-means here. So k-means is nothing but clustering. Clustering is nothing but segmenting, putting certain data points into different clusters. But in segmentation or clustering, we don't know how many clusters it can be converted into. So essentially there are, three types of clustering. One is k-means clustering, one is hierarchical clustering, and one is DB scan. So DB scan is one of the more advanced algorithm. Hierarchical clustering and a normal k-mean clustering are two sides of a coin actually. One is top to down approach, one is bottom up approach. So top to down approach is you start randomly. In case of k-means, you start randomly. So K is basically your number of clusters, and means is because it works on a concept of centroids or a mean. It works on a concept of means actually. So that's how I think the name is k-means. In k-means, the approach is top to bottom. Yes, the approach is top to bottom. So what happens is you start randomly. That hey, you start with a random n number of clusters, like 3. So basis that 3 cluster, you try. So again, there is a different mathematical equation to it. Okay, or a formula to it. So it will try to find that value which is coming through that formula. And depending upon the case, whether we're trying to maximize it or minimize it, it will come to a decision that, hey, whether these 3 clusters are giving me that maximum value, but I want the minimum value. So what it will do, it will, change the locations. I mean, it will maybe increase the number of clusters and then again calculate some error. So the error term is actually called sum of squared errors actually. So for example, how do I put it? Okay. So let's suppose the distance between my home and the airport is 35 kilometers. And it's trying to put my home and the airport into same cluster. And then it calculates and let's say airport is the center of that group, let's say. So what it'll try to do is, for all the homes that it has predicted in this same cluster, it will try to find the distance of it from that airport. And that distance will be squared and added, and a number will come. Okay. Now what it will do is, it will change the radius circle to some other dimension. Let's say initially it was 15 kilometers. It takes it to, like, let's say 5 kilometers, and maybe now while I was assigned to airport A, I get assigned to airport B, and my distance will be calculated again from airport B, and other homes that got into vicinity of airport A, all the distance between from those homes to airport will be calculated, and that will be added up. So at every iteration now, these distances are squared up and added. So whichever groups give the least number of that distance now, those are considered that those are the closest ones to each other. So at the end, it uses a distance formula between a point A to a point B. And distances can be of two types. Like we have either a Euclidean distance or a Manhattan distance. So Manhattan distance is basically a block distance. So it's based on the city called Manhattan, where the city is divided into blocks. If you want to go from A to B, uh, but there is no straight way between it. It's like either you do like this, like you're moving on the points of graph. So that's how Manhattan distance is, and one distance is Euclidean. See, at the end, whichever distance we are using, our goal is to make sure that whatever clusters we have formed now, those should have minimum distance between each other. And now one question should come up: what is this? How is this distance calculated? So, for example, let me go back to that original example of salary. So let's suppose you have data of certain candidates where you have experience, you have degree type, no, years of education. Let's call it years of education for sake of simplicity. And the third could be experience age, or the third could be, I would say, distance to their office, maybe. I'm just assuming a hypothetical example. It may have or may not have relevance to the salary of a person. Now you're trying to, cluster them up. Now, experience will have a numerical value, right? It will become a point X on a hypothetical scale. Years will have a value. It will become a point on a Y on a hypothetical scale. The distance to office will become a hypothetical point called Z. X, Y, Z is a point that denotes on a three-dimensional figure, three-dimensional plane, just assume. So that's how you have all the points. And you have a numerical value to it. So 1 comma 2 is what? X is 1, Y is 2. 1 comma 2. 1 comma 2 comma 3 is X is 1, Y is 2, Z is 3. So that's how you have n dimensions plane, and it becomes a vector. And using the distance formula, we can calculate distance between 2 points, whether they are 2 points or 3 points or 4 points. So that's how it works in a mathematical fashion and tries to find the number of clusters. Now, that's about finding the closest observations to each other, but how does it decides how many number of clusters it should have? Okay, so as I said, the term sum of squared error, it will start with 2 clusters, find all the distances, put down a number, let's say 100 at n is equals to 2, k is equals to 2. Then it will go to 3 clusters. It will find all the sum of squared errors and it will list down a number. Let's say 80. So essentially, number will not increase, it will decrease. So that's how the algorithms work. They converge, they do not diverge. Then at 3, let's say it comes to 70. At 4, let's say it comes to 60. So it's linearly decreasing. And let's say at 5, it goes to 30. So that linear fashion is now broken. From a decrement of 20, 10, 10, and suddenly 30, I see a huge drop in that distances. So something breakthrough has been achieved. Now, I will try it and k is equal to 6 as well, and I might see a drop of 5 only. So a certain kind of, a elbow will get created in your graph. This elbow, so this chart is essentially called a elbow chart only, where it is plotted between, so it's kind of a scatter plot, you can say. It is plotted between number of clusters and sum of squared errors. And this elbow gives you an idea of, hey, at this number of k, I have the maximum separation in my data. So maybe I have the maximum number of clusters already with me at k equal to 6. That's one of the popular way to identify the clusters. Now, see, clustering doesn't end here, okay? And that's not the end of it, how you determine the quality of clusters. You have the number of clusters, but you have to essentially determine the quality of the clusters as well. So in the world of analytics, what we do is, once we have, let's say, 5 clusters, we do certain kind of RFM analysis, you can say, recency, frequency, and monetary value to it. But RFM analysis doesn't have to be on recency, frequency, or monetary value. It can be on anything. So once you've defined a consumer segment, you can look at, what's the average age in that cluster. So you can define certain metrics, and then you try to see, hey, for the certain defined metrics, do my clusters really differ? So at k equal to 5, there's a very high chances that cluster 4 and cluster 5 have similar average age. They have similar gender ratio. They have similar, median income in that. And maybe when you launch the product, you might observe. So, okay, let's not launch the product. So since now we have the clusters, let's look at the past data, how these clusters have behaved. So basis the past data, you might see that cluster 4 and 5 are behaving in a similar fashion. So maybe it is possible that cluster 4 and 5 are not 2 separate clusters, but 1 cluster. And counterintuitively, it can also happen that cluster number 1 may not happening in the same fashion over the period of time. So maybe there might be a subcluster in it. So elbow method is never the best way. It's one of the way technically to reach to the number of clusters, but it's not the best way. So now we can never have this much data that I'm talking about, and we might not have this much leeway as well. So one way to solve this is another technical method called silhouette score. So what silhouette score does is it again uses a mathematical formula. If I'm not wrong, it's cohesion minus separation divided by cohesion. And so it basically takes that what's the difference between all the points in the cluster, basis that X and Y, the data points that we have plotted, and what's the difference between to the what's the difference of that data point to the nearest next cluster, center of that next cluster, and we'll try to find a number. So eventually it is done for all the eventually it is done once you have all the clusters listed down. A silhouette score comes in, and it's I think become it's between 0 to 1. You can probably Google it out if I'm not wrong. It's higher the better actually. So higher the number is closest to 1, we say that there is maximum separation between the clusters, and the quality of clusters is good. So this is also one way to examine the quality of clusters. If you are not able to do the RFM analysis, never stop at elbow method, go for silhouette score as well. So that's about the top to bottom approach. So another type of clustering is hierarchical. So hierarchical clustering also, calculates certain kind of distances, which is called linkage. You can check the definition of linkage. It's another way to calculate the distance actually between 2 points. It can be simple linkage. It can be complete linkage. So there are two ways. See, either you minimize something or you maximize the negative value. If I'm maximizing the negative value, that means something which is at 15, I'm trying to go towards 0, and then I'm going to go towards the negative aspect of it. So eventually I'm trying to minimize a distance. So simple linkage, double linkage, they work in the similar fashion. How hierarchical clustering is different from this k-mean clustering is that, let's suppose you have 100 data points, it will assume all the 100 data points to be as 100 clusters, and then it will start calculating the distances, and whichever distances are the closest, it will start mapping those to the same clusters. So eventually levels get created that, okay, at level 100 I had 100 clusters for 100 data points. At level 99 I might have 50, because 50 49 got one different clusters, and 51 got mapped in one cluster only. Suddenly it can happen very well. So that's how hierarchical clustering works. Now another question is, how do we decide optimal number of clusters in hierarchical clustering? Is one is again kind of a similar, there's a linkage plot you can use, which is, so basically we are looking for that drop, actually the drop in the squared error, the time it will give a sharp drop. That's the number of clusters that we're looking for. In case of hierarchical clustering, however, what we do is, I'm just giving an example. See, there is always a subject matter expertise to any expert. Never rely on machine learning 100%. Never rely solely on it. So what we do is, so I work with KFC. Okay, so we do clustering for KFC stores. I know there are 1,000 stores in UK, and my elbow method is suggesting 7 clusters. But eventually, I end up keeping 11 clusters. Why? Because my elbow method was suggesting 13 clusters, but I end up keeping 11 clusters. Why? Because 12th and 13th cluster was coming like, only 7 stores in it, only 9 stores in it. So you always need to put some business knowledge to it, that would it make sense to keep 9 stores into one cluster? I did the RFM analysis. I didn't find anything. Anything special about it, that why should we keep it in a different clusters? But technically elbow method was showing 30. So never rely solely on the clustering techniques in that sense. Always apply your business knowledge to it as well while using the algorithms. So any questions on clustering, anything?
So basically, clustering is nothing but we are trying to classify the objects on the basis of similarity and dissimilarity. you're saying?
Yes, yes, exactly. Very good point. Either similarity as well as dissimilarity. So it's not just similarity; it's dissimilarity as well. So when we say there's a drop of on the elbow plot, at one point we're trying to find the similar stores or the similar clusters, and at the same point we're trying to find there's a maximum separation between the clusters. So basically, there are two clusters. In every cluster, there are certain points. So for those points, that distance should be minimum so that there's maximum similarity. But between those two clusters, there should be, maximum separation. So yes, we try to find certain groups basis similarity as well as dissimilarity.
Okay. And for the k-means algorithm, we are trying to, basically like trying to categorize k in terms of partitions, right? Where like,
Yes. Yes, it's kind of a partitions only. Yes, it can be linear or non-linear, but yes, at the end, it's partitions. For
o-
classification, also it is partitions. Actually,
and
if you just look at like yeah. Sorry, please complete your question first.
yeah, so we are trying to classify it into, algorithm partitions, and then there will be clusters where in which there will be observations which will differentiate basis on the, you took the example of Manhattan city as an example, right?
Yes.
So there will be a nearest serving as like reference to the cluster.
Yes, in a way, so ideally what would happen is all the observation that lie in a cluster, they will have similar property. So I'm not saying they'll have the same average salary, but it will be very close. It's like 1 or 2 standard deviations away. So 97%, yes. If I apply the empirical formula, they will lie very close to the mean. So let's say you talk about the average sales of the stores or their average weekly sales. Let's say the average weekly sales is 35,000 pounds for that clusters. So not every store will have 35,000 pounds, but yes, it will be very close to the mean, either 33 or 37. So yes, they'll be very close to each other.
So the mathematical formula in the k-means clustering algorithm, does it involve n observation and k clusters?
N observation is not taken, but yes, it asks for k initially from us as well. So ideally,
Okay.
since it's unsupervised, but it asks for k from us as well, so that it can evaluate. It's able to plot, it's able to find the elbow plot for us. So you can give k like 50 as well, and you can look at the long picture, the big picture, where the elbow is actually. So it can be at n k equal to 25 versus it can be at k equal to 6 as well. But that's not the end of it. After elbow method, you have the clusters. Always go for silhouette score.
Okay, so in terms of example point of view, can we take earthquake as an example for this, like studies of an earthquake?
So what's the problem statement? I mean that
Like
when the
we
earthquake
are
is going to
trying,
happen.
no, we are
Huh.
trying to actually know the affected regions of the earthquake. Classifying them into the, you can say, hotspots or dangerous zones.
You can, yes. In that case, you can, yes. So I'll give you a very good example of it. So
Hmm.
once you have done the clustering now, so basically you have given the labels to certain unlabeled observations, right? Now, going forward, if you want to check about a new region, whether it's a high prone to, it's a red zone or a orange zone or a green zone, you don't have to go for clustering again. You can use a classification algorithm on top because you have already done you have already labeled certain zones. So at first, if it's starting from scratch, you will do clustering, but going forward, you will do classification.
Okay, so our first approach will be clustering, you're saying?
Yes, it should be clustering, and then it should be classification. Those two models should be in play. One is clustering, and then for every new for the output of clustering, a classification algorithm should be trained, and for every new prediction, it should pass through that classification algorithm. so that it can classify it in advance, that whether it will belong to cluster A or cluster B. And eventually, over the period of time, let's say 1 year or 2 years, I'm not sure when you update your data, you should reevaluate your clusters. So let's say essentially you started with 4 clusters, they can be they can get converted into 3 or they can be 5 as well. So clustering has to be revisited again and again with new data. But yeah, that's how I would solve the problem.
Okay.
Yeah. So I don't have any more content to share, but you are free, just feel free to ask the questions, or we can close this at any point.
Is there any point where we have to see the data and your all learnings over there?
Could you elaborate more? I mean, see, you look at the data when you get the data. You do exploratory data analysis. You look for duplicate values. You look for missing values. You look for completeness. But what exactly is your second part?
No, I'm just saying as you teach us like a theoretical, and we learn more many things with about this tool throughout your teaching skills. But somehow, if you show some data, get some data and show the algorithms throughout the practical, that would be better to understand.
So yeah, that would be the best actually, I would say. So I would, recommend you can like go to YouTube as so I mean I'm sorry, just don't take me wrong. Do you want me to teach this, or do you want for a way to find out how you can make your learning more more robust?
I'm just saying whatever you have the data as you working on the same things, you can show that kind of working so that
I can show you that. So okay.
If you have any confidence
I have.
that I am okay.
I have. No, I have actually. I have a blog as well. Actually, let me give you a link for that. So on that blog now, I had started it a year ago. There's a lot of recorded material, but I was never able to, put it online. Just give me a second.
That's great. You can share with us so that we can correlate
I'm
with
just
our
sharing.
data.
So I had recorded the algorithm actually, logistic name base. I remember specifically all the decision trees were covered. I'm just looking at my blog right now that did I put it online or not? Which because I didn't get time.
It's not about IIM paper and all these things. I just want to be implemented in my working. That's why
Exactly.
actually Excel. I can do anything in Excel, right? But
I
somehow
get
this
it.
is a good
I
tool
get it.
understand the data.
So I actually prepared all the blogs in Python, but I think you are hoping to work it in Orange, right?
Yeah.
Yes, you need to. So eventually, I don't have anything in Orange, but maybe yes, I can maybe take a class next week if you want for the Orange. I can maybe show you on live.
Yeah, it will be
So
better.
see, I can take the class. It's totally fine because we do use Orange. I'm working in data science only, and my other team members who are the business users, they use Orange actually. So they use Orange to run decision trees a lot. So maybe I can maybe record a session, or maybe we can do it in a live manner. We can do that surely.
Okay.
Let's do it next week. Yeah.
Is this really beneficial for the higher management?
I think we have exam on Saturday. That is
Yes.
everybody wants to,
Yes, Survi.
So I mean, do you have to do a practical as well?
I'm not sure.
I don't think so.
Actually, I've attended
Yes,
the
you don't
language
have to.
session. So, could you guys please help us to understand how the exam would be? Like, will it be some practical kind of thing or just MCQs?
Surbi, from what I know, I think it should be just MCQs, not the practical.
It's only MCQ.
Even better, yes. I saw the curriculum. It won't be practical because it's a certificate program, which already says it's advanced general management. But sir, coming to a question that whether it is good for higher management or not, it would be really beneficial for you to learn Orange because it is more of a plug and play tool. You just have to drag and drop and you get the results quickly right away. You don't have to wait on a team member. If you have a presentation, you can have certain, insights already with you. So it's always good to have. But again, it depends whether you are from analytics, if you are in analytics services or not. So if you're coming someone who is in operations, does he has to learn or she has to learn Orange? I won't suggest so. But if you're coming from consumer research, I would advise yes.
Yeah, somehow we are presenting some data and we have to analyze our channel. Actually, I'm heading of operation and supply chain for the footwear brand. So somehow we have to be analyzing things. But I have managed in Excel myself. But when I had used Orange after this IIM class, and I have set some throughout that data and other things. But I think I don't know about whole tools whatever they are providing for analytic skills. That's why there's a limitation,
And so may I know what problem were you trying to solve through?
So basically, the cluster and all this kind of things.
Clustering,
and
yes, yes. Themes, yes, very good. Yes.
How we can reduce the timing period for, if I'm the footwear industry, I want to see the trends, what we are selling it right this month, and what will be the next year, what we have to purchase from factory. So this kind of working we are doing in Excel for the current data and standards. But we have sold out in this.
I think you should definitely use it. I mean, you must be using forecasting as well. I mean, in operations, forecasting is very popular, and the themes that we're trying to find, you should use Orange for that. I think yes, for forecasting, for finding out themes. So themes can be like themes of footwear, I suppose, that what footwears are getting into what themes, or the themes of customer, what they are buying currently.
Yeah, right.
Yeah, it is. I think it will be helpful for you. Yes, that is.
And definitely, I will spend my time in this, and I have to learn because I'm not technical person to do Python and all this JavaScript.
I get it. So that's why we have tools like Orange because they give very good results. I've seen personally, and I am also. I'm in products as well. So you use Python for that. But for any analytical problem, like that we have to solve, we don't go to Python. We use Orange. So yes, it's a very good tool. And
my organization, can you please share me your contact detail if you want, so that I can connect with you?
Sure. So, what do we need? I mean, should I write my email or what?
Whatever you, mobile number and email
Let
ID.
me write down. Let me write down. Let me write down my email.
So definitely,
let's connect on LinkedIn. I think that's the best way to communicate.
Somehow we are training to my team members, so I'll connect with you guys, and that will be in the paid services. We have to take you in office, and you have to be teach us some technical thing.
Okay, sure. No worries. Paid thing, I'm not sure if I can accept any payment, but yeah, I'll love to do a session. So, sure.
That's great. Whatever you feel good.
Yeah, sure. Definitely, I can. Looking forward to
it. And your kind support and to meet with such kind of fantastic person, Sachin.
Thank you.
Thank you, Sachin. Thank you.
Thank you so much, Sachin, Surbi, for organizing this. Thanks a lot.
Thank you,
I hope it adds.
Where's the link or your number or your thing shared? I can't see it here.
It's in the chat.
Just hold on, we'll
I can't
note down the number.
Actually.
Okay, so maybe Surbi can communicate further. So also, if you have any questions now, feel free to, write me an email or something. Just feel free to do it on WhatsApp as well. Not individually. I think we can create a group and you can ask the common questions, not just related to data science. You can talk to me on anything like team management. So I'm a people manager as well. You can talk to me about product ownership, product development. I've recently done this certification from Scrum, and Yes, and
Anything can
about
be done. Anything can be
analytics in
done.
general.
Anything can be done on the production, like manufacturing industry, Sachin.
I love to sit down with you, Sarfaraz, and explore it. Definitely. I haven't done it because I come mainly from financials and QSRs. QSR is basically quick service restaurant. So we can definitely sit and maybe explore. So I have a good peer network. Maybe we can solve a problem. Definitely. Yes.
Yes, sure. It was nice meeting and a lot of learnings.
Sure. My pleasure.
Thank you so much, Sachin. It was
All
really
right.
glad meeting you. Good night.
All right.
Thank you.
My pleasure. Thank you. Bye bye.
Thank you,
If
Sachin.
someone can
Survi.
send in the